Hi, my name's Brian, and this is the first part of a two-part series where I talk about the LED strip lighting that you can get in those, like, typically 5-meter spools. You can get them on eBay for, I think, some as little as about $10 for 5 meters. More typically $20 and sometimes a bit more than that. And you can buy them from other retailers that are specifically lighting related, and they typically are considerably more expensive, 4 or 5 times as expensive, sometimes more. In any case, the reason why people use them is they're very versatile. You can do a lot of things with them. And my sort of interest in this started a few months ago as I was doing some more video and I needed to make a light panel for video work. And I found a video on YouTube from a channel called DIY Perks, and it looked like a nice project, so I went ahead and ordered some parts and put together a light panel. Somewhat different than the design that the DIY Perks did, but of a similar concept. Basically, you're running multiple strips in parallel and then joining the ends electrically to power them. So I tested that out, and I discovered very quickly that the 100-watt buck converter, the power supply inside the unit that powers it, the one specified at DIY Perks, is kind of inadequate for the amount of power necessary to drive, for example, the system that he had specified, which was 15 meters or 3 5-meter spools of LED tape, to run that at 12 volts, which is the maximum rating for the LEDs. To run 15 meters of those tapes at 12 volts, cut into 500-meter lengths as he had them, you'd be running around 180 watts or so from a 100-watt buck converter, and that's just not going to work. This particular one is 10 meters, so only 2/3 of that. And I had measured upwards of 120 plus watts total power consumption when I turn it up to 12 volts. And so I don't turn it up to 12 volts. But I also have made some modifications that provide active cooling of the buck converter. And I'll show you that in some greater detail in a little bit. But there's some additional things that you can do with LED strip lighting. For example, this overhead light here, and I'll show you pictures of that in a minute or two. I just built this recently with 3 strips, 750 millimeters long, and I have that powered, again, with a small buck converter, and powering that with a cheapy Amazon, like $5 or $6 replacement laptop power supply, which puts out like 19 volts DC. So 19 volts DC powered, put into a buck converter, and then I can control the voltage from 6 to 12 volts thereabouts. And that's true with both the LED light panel, and this is the first one I made, and frankly the quality of the LEDs I did not like very much. It's too blue, and there's a rubberized plastic coating over the strip, and you'll see that better in part 2 of this video. That is, I presume, for waterproofing, water resistance, whatever. But in order to attach the wires to them to power it, you got to cut off those little rubber ends on both ends of every strip. And I've got like 25 strips here, So that's a pain in the butt, a real pain in the butt. And again, the light output I didn't like very much, so I purchased a second tape, couple of spools of tape, and this is some of that. It's a different series, but by and large, you get the tape on these spools, and you can cut them at basically every 50 millimeters. There's little marks on it that shows you where you can cut them, and then you can build a light panel like this, or an overhead light system, or pretty much anything you want. For my light panels, since they can consume a lot of power, basically upwards of 100 watts, and a bit more than that for short-term use, that's a lot of power. And I really intended to build these to be battery powered. And fortunately, I have some really good batteries to drive them. These are DJI TB48 batteries that I use for my Inspire 1 Pro drone. So it's like 129, almost 130 watt hours, and 20 to 26 volts. It's a 6S battery. So this provides a great voltage and power capacity for the buck converter, fully within the range that the buck converter is designed to handle. So a great match for it, and I'll quickly demonstrate just by plugging it in. I had to make a connector to plug this in, and so let me just plug that in here, turn it on, and you can see it's got 3 solid LEDs on it, which basically tells me this battery is about 3/4 charge. So I'll go ahead and turn the light on, and you can see that's actually at kind of a low setting right now. I'll turn it down even more. So at very low voltage, you can see not all the LEDs are on, and some of them are actually fairly bright even at that point. So they're not all of equivalent vintage or capabilities. At this price point, they're not going to do really accurate sorting to match them properly. But once you get above about that point there, and I'm showing about 8 volts, and at 8 volts you're putting out very little power anyway, very little light anyway. It's not really until you get to about 9.5, let's go to 9.5, okay, 9.5 volts, and that's a decent amount of light, but just getting to the point of being decent. Anyway, I'll shut this off so it's not glaring, and shut this off, and unplug it. So one of the things that I didn't like about these LEDs, as I mentioned, was the color. It's too blue, and I'm guessing it's in the 5500-ish Kelvin range. But the specifications from the manufacturer, at least as they were listed on Amazon, said like 4,000, 4,500. So clearly not accurate. But as you can imagine, a lot of the stuff on Amazon, a lot of the stuff coming from Japan directly, or more or less directly, you have to take the advertised specifications with a grain of salt. And one of the problems with these LED strip lights is that particularly the power rating, and related to that the current rating, is very deceptive. For example, a 5-meter strip of spool of LEDs, the full 5 meters, which has like 300 LEDs in it. If you were to plug 12 volts into it, power it from 12 volts, it might consume about 34, 35, 36 watts. All right? But if you took that same 5 meter tape and cut them into 10 strips half a meter long, and then powered all of them from 12 volts, your total power consumption, even though it's exactly the same number of LEDs and the exact same total length, but by cutting them into shorter segments and powering them individually from 12 volts, now the power consumption just about doubles. Just about doubles. Now that's important to consider when you're doing a project and you need to specify or select a power supply to drive it. Because if you just take the raw number from the full tape at 34, 36 watts and assume you could cut that into 10 pieces and then power it from a 12 volt supply and only need a 30 or 40 watt power supply, you're going to be in trouble, because that's not going to work. So in part 2 of this video, which comes up in a little bit, I'll go into greater detail of the design of the strips themselves, both types. I'll put them under a microscope, and you'll be able to see how I trace the circuit of each of these tapes. And again, as I mentioned before, in most cases, these 5-meter tapes can be cut at basically 50-millimeter intervals. Now, there's some variation. I think there's some tapes as little as 25 millimeters or an inch. But 50 millimeters seems to be about the most common. Pretty much all of them, or just about all of them, are that way. And that allows you a lot of flexibility in how you use these. You can cut them to as little as one 50-millimeter strip, or as long as 5 meters, or you can actually attach them together and make them longer than that. But bear in mind the voltage drop if you attach and connect them in series is just going to get worse and worse and worse. A 5-meter tape connected at one end from 12-volt supply. So you're feeding 12 volts into one end of it. At the other end of that 5-meter tape, the voltage isn't 12 volts anymore. It's more like 9.8 or maybe less. So you have a lot of voltage drop, and if you attached another piece of tape to the end of that, then it would get less and less and less. So you don't want to do that, but you need to take that into account. So, and one of the things I had to do to sort of compensate for the color temperature of the LEDs in this, and you can probably tell there's kind of an orangish hue to this. So I have I think it's an 1/8 stop orange filter behind this, and it helps, but it's still not great. So what I'm eventually going to do is replace the LED board itself. And the way I've designed this box is that the LEDs are on a single, in this case I think it was a 1/4 inch piece of MDF, and so I can just basically disconnect that and then slide that panel out and then put another panel in with the newer type of LEDs, which I eventually will do. So let me give you a little closer view of how this is built, and let me pause it for a moment. Alright, so again, this is the business end of it, and this is the back end of it here. So I have the connection for the battery, goes in, and the hot side, the plus side of the voltage, goes to a fuse, then to a power switch, and then to the buck converter. I have a potentiometer to control the voltage and therefore power to the LED itself, and I have 2 volt displays, 2 voltmeters. One measures the voltage coming from the battery, so I know what the battery voltage is, and the other one displays the voltage set point for the LED itself. So let me go ahead and open this up, and let me pause it, and I'll start it again when I've got it opened up. Okay, I've got the screws loosened at it, and I'll open it up in a minute, but first of all, I have the openings here for a 120 millimeter fan, which is pulling in air. The buck converter is mounted to the board right here. Tilt that up so you can see it better. It's mounted to the board right here, and then I have holes beside it so that the air that is being pulled into this basically plenum area, some of it has to vent past the fins of the buck converter, which actively cools it. So this gets very effective active cooling. You'll also notice I have holes at the top of this LED panel, and that's to match with the holes I have at the bottom. So again, that 120 millimeter fan brings in cooling air into that box area, basically a plenum, and a good deal of that air comes through these holes at the bottom of the LED panel itself, and then washes upwards and is vented out the top. So the panel gets active cooling from that fan. Okay, so let me see if I can open this up. Okay. So fan I have here, obviously. I have a buck converter for to drive the LED panel. I have a little a smaller buck converter for the fan, which I didn't really need, but it's there anyway. And some terminal boards to tie everything together. So again, the design is such that I can disconnect this wire and slide this panel out. I have to take the top off, and that's not hard to do. It's just 2 screws, and then this comes off. And then I can replace this entire LED light panel with a new one with better LEDs. And one of the things that I'm going to do as a modification, an additional modification, is to make larger holes for the cooling. So that's the design of it. Again, active cooling. Air comes into this sort of plenum box, and I've kind of sealed around there with some tape, so it's decently sealed. So the air goes in, it's got to go out. So some of it goes past the fins of the heat sink on the buck converter, which actively cools it, and it does a very effective job. I could legitimately overdrive this to probably 120 or more watts if I wanted to, but I generally don't do that. And then, of course, the bulk of the cooling air actually goes into the LED light panel area at the bottom, washes up, and then vents out at the top. So that's the design of that. And again, I'm not trying to point any fingers in an accusatory way at the guy at DIY Perks who, it would have been nice if he had gone into some greater detail about the current requirements and how that's going to be greater than the buck converter. And this is actually the buck converter he specified for that project. It's rated at 100 watts. And so, again, I'm not trying to point an accusatory finger towards him. I think he did a nice job with the design of that. It's just the little details, and the little details that matter. It matters if you're going to be building a panel or some other light project yourself, that you need to understand the relationship between the length of the strips, the number of strips, and the current and power requirements to drive those. Let me tilt up so you can see the work light I built for my electronics lab here. And again, I used LED strip lights, a total of 3 strips of 750 millimeters each. And I have a control panel here, and I'll show you that in a second, where I can vary it to a little over 12 volts down to basically 6 volts where it's shut off. And for me, from about 9 volts on up is useful. Much less than about 9 volts, and it's really not doing a lot. But the control panel for that is this guy right here. And you can see it's right now showing 9.2 volts. So what I have basically in here is another one of those little buck converters. And that's being powered from like I said, like a $5-6 Amazon special laptop replacement power supply, which outputs 19 volts. That comes into here. I switch it on and off here. Then it goes to the buck converter and ultimately out to the LED panel. I have also a small 40 millimeter fan to help with the cooling, although given the very low power consumption of this LED overhead light panel, which maxes out around about 40 watts, the buck converter is not being taxed. It's again a 100 watt buck converter, so over spec for what it needs to be for this particular project. But I put a 40 millimeter fan as a cooling fan in there anyway, just as a safety measure. And I put like 3 or 4 diodes in series to cut the voltage to the fan to slow it down. And it's on right now, and you really can't hear it. That's max, and it shows 12.5 volts, but that's 12.5 volts output from here. At the LEDs themselves, that's like 12.2 volts given the voltage drop. So I more typically keep it around 10 to 11 volts. That's sort of the sweet spot for me. Anyway, that's another one of the projects. And my other light panel, and the one that I'm actually using for this project, and I'll zoom in a little bit, and it looks like it's not too bright there, but the camera is adjusting its brightness to compensate. So zooming out, you can see how that works. So looking above, and I'll walk in, you can see that I have the battery that's the drone battery that's powering it, and there's 4 green LEDs, and the top one is flashing, which tells me that it's between 75 and 100% charge. So, and with this battery at the typical, voltage and light outputs that I operated at, I can get sort of a minimum of about an hour, but upwards of 2 to 2.5 hours, even 3 hours at the lower settings. If I turned it all the way up, which would be overtaxing the power supply a little bit, the buck converter, I would be down maybe 45-50 minutes. But I don't run it there anyway, so. Okay, in this segment here, I demonstrate how I measured the voltage-current relationship of all of the lengths of LED strips. And in this particular demonstration here, I'll just show you for a piece of 800 millimeters in length. But I did this for all of the lengths from 50, 100, 200, 400, 800, 1600, 1300, 3200, and 5,000 millimeters. So there was, numerous tests at different lengths, and I measured the current voltage relationship with a voltage input to the tape at 7 volts, 8 volts, 9 volts, 10 volts, 11 volts, 12 volts, etc. So I record the current value I get, and I can see that from the power supply. And I also record the voltage at the other end of the tape. So I'm injecting, let's say, 7 volts at the input side, where I'm applying the voltage. But I'm also measuring the voltage at the other end of the tape to account for the voltage drop on it. Not noticeable so much with an 800 millimeter, but as you get longer and longer, then that effect gets more and more noticeable. Anyway, we'll start at 7 volts, and I'm right at 7 volts. And I have the 1 meter here. The bench meter is showing the voltage going into the tape, and the Fluke 27 is showing the voltage at the end of the tape. So at this point, at 7 volts, the LEDs are really not even on at this point, so there's essentially no current flowing. And as you can see, I'm showing 0 current, 0 milliamps. So I'll write that down, 0 milliamps, and 6.99 volts is the voltage as measured at the end of the tape. So now I go to 8 volts. So I'll set the 8 volts, and okay, we're at 8 volts, and I'm showing a current of 24 milliamps. So 24 milliamps, and a voltage at the end of the tape of 7.99 volts. Okay, now let's go to 9 volts. Okay, now I'm going to have to tweak the voltage a little bit because I'm getting some voltage drop going into it. So let me tweak it up a little bit so I get pretty much exactly 9 volts going in. Okay, that's as close as I can get it. So 9 volts going in, I'm showing 168 milliamps, 168 milliamps, and 8.97 volts. So you see the voltage drop is starting to increase. Next voltage, 10 volts. Okay, and again, I voltage drop going into the tape is even more noticeable as we go up higher. So I have to again tweak the voltage. Going in to get it to be at the right voltage, and that's 10 volts going in, and I'm showing 356 milliamps and 9.94 volts at the end of the tape. 11 volts. And again, I'm going to have to tweak this. And getting up around 11, 12 volts, you should wait a little while because now we're getting some heating effect, and the voltage current relationship of the LEDs changes a little bit as they get warmer. So you really should record it after it's kind of stabilized. If you look at the currents showing 575 milliamps, and now it's increased a little bit. So let's wait just a little bit here. I'll maybe stop this and then restart it and when this is stabilized. Okay, I think we're about as stable as we're going to get. We're reading just a hair under 11 volts on the input. If I tweaked it up, it would be, you know, a little bit more than that. So we're at 588 milliamps, and I'm showing 10.90 at the output. Alright, similar deal with 12 volts here. It'd probably be more noticeable, and again I'm going to have to tweak the voltage because of the voltage drop increasing. And I'll let that stabilize, and once again, let's let this run for a bit. We're at 825 milliamps, and we'll probably have to wait a little longer. I'm going to guess it'll stabilize around about 840. So again, I might cut away from this so you don't have to just sit there and watch, and come back when the current and such has stabilized. Alright, well I think we let it run long enough. It'll probably drift up a little bit more from here, but probably not a great deal more. So we'll record this as 844 milliamps and 11.86 volts at the other end. And let me just shut this off. Okay, so again, I've done this same experiment with other sections of this LED tape, and section at 50 millimeters, another one at 100 millimeters, another one at 200 millimeters, on up through 3200 millimeters, and the full roll at 5000 millimeters or 5 meters. So I then compiled all this information into a table, and we'll take a look at that next. Alright, so this is the compiled table with the data from all the voltage current tests done with tapes at 50 millimeters in length, 100, 200, 400, 800, 1600, 3200, and 5000 millimeters in length. So 1, 2, 3, 4, 5, 6, 7, 8 different lengths of tape, and at 7 volts, 8 volts, 9 volts, 10 volts, 11 volts, 12 volts, and in the formal test I did that this data was compiled from, I also went up to 13 volts just for S&Gs. So in this top table, I'm monitoring the current that's drawn at those various voltages and lengths, and also the voltage that's measured at the other end of the tape, so we can see what the voltage drop is. In the table below that, I basically massage the data from this table so that I calculate what the current per meter length is for all of those measurements, so that I can see how the current per meter varies with voltage and with the length of the tape. I also then took the voltage at the end of the tape and subtracted that from the voltage input to get the actual voltage drop. So we'll go over that in a little bit. So as an example, at 12 volts, the current at 12 volts and a length of tape of 5000 millimeters, the full length of the tape, the current is 2.867 amps, and the voltage at the end of the tape is 9.710. So looking at the table below that, that translates to a current per meter of 0.573 or 573 milliamps, and a voltage drop of 2.29 volts. And you'll notice at the same 12 volts, the 50 millimeter length of tape, the current is 52 milliamps and the voltage is 12 volts. So basically 0 voltage drop. With a very short tape, first of all, the total current is very low and you have very little distance in which to drop voltage. So you have very little voltage drop. But the other interesting relationship is that the current per meter is much higher with a shorter tape than it is with a longer tape, and it just gets it's 1.04 amps per meter, 1.08, 1.065, 1.06, 1.028, 0.955, 0.760, 0.573. So other than the first reading, which is a nominally a little lower than one would expect, but when you're only using 3 LEDs, sample variation comes into play there. So by all rights, it would very likely have been higher than the 1.08, probably more like 1.1 or 1.09, something like that. In any case, you can see that the current per meter is greatest at the shortest end, where the tapes are shorter, and the current per meter is least with the longest tapes. Again, owing to the voltage drop. Again, you could see the voltage drop at 5,000 millimeters, at 5 meters, is 2.29 volts. The voltage drop at 50 millimeters is 0. Basically no voltage drop at all. So if you're not losing voltage, you're getting the full current. And that's sort of the relationship. And where this plays into the equation is that if you're figuring on a power supply based on the current voltage relationship of the full length of a tape at 573 milliamps per meter, but you cut the tape into smaller sections, and you should be figuring more like an amp per meter, you could very easily underspec your power supply for your application. So that's really what I'm getting at here. Okay, so this ends part 1. In part 2, I'll continue with a little more detailed inspection of the tapes under a microscope. So we'll see you there. Thanks for watching.